Capacitors work to store energy by stretching the orbits of electrons in a dielectric compound between a positively charged plate and a negatively charged plate. As charge accumulates on the positive plate, the electrons of the dielectric material gravitate toward the positive plate, distorting their orbits. The attraction of the nucleus to the negatively charged plate further stretches the atoms. This process of distorting the orbit of the electrons uses energy that then becomes stored in the dielectric material. A capacitor must be attached to a closed circuit with an energy source, such as a battery, in order for it to store energy. When the switch is closed, electrons flow and charge builds up on the capacitor's plates. This causes the voltage across the capacitor to increase. Eventually, the voltage across the capacitor will equal the voltage of the sources. At this point, the flow of electrons stops because the source voltage and capacitor voltage is equal but opposing each other. The capacitor is essentially charged. All capacitors charge at the same percentage rate. Based on the universal charge curve, after one time constant, the capacitor will have reached 63.2% of its potential, 86.5% after two time constants, and so on. After 5 time constants, the capacitor has reached 99.3% of its potential and is considered essentially charged. A time constant in seconds is equal to the resistance of the circuit in ohms multiplied by the value of the capacitance in farads. For example, in this circuit, if you have a 1 megaohm resistor and 5 microfarads capacitor, the time constant would be 5 seconds. Therefore, for each 5 seconds of elapsed time, the capacitor will achieve its corresponding voltage percentage until it reaches an effective charge after 5 time constants.